In our previous videos, we mentioned that positive sequence, negative sequence, and short-circuit impedances are often equal for the transformer. In power system analysis, short-circuit impedance is the most frequently used parameter. But many junior engineers are misled by the name, thinking it only exists when a short-circuit accident occurs. Today, we will start from the engineering definition, use the T-equivalent circuit, and explore the physical essence of short-circuit impedance. We typically represent short-circuit impedance as a percentage voltage, denoted as ZK or UK%. According to the measurement procedure in IEC 600761, short-circuit impedance is defined as, at rated frequency, when one winding is short-circuited and voltage is applied to the other winding, the ratio of the applied voltage to the rated voltage when the rated current flows through the windings. Usually, we short the secondary side and apply voltage to the primary side. The formula is UK equals USC over UN. USC means the voltage applied to the primary side. UN means the primary rated voltage. To simplify complex electromagnetic induction of transformer, we use the T-equivalent circuit to represent transformer inside impedance. The left branch represents the primary impedance. The right branch is the secondary impedance. To analyze the circuit by bringing both windings to the same voltage level, we need to refer the secondary side impedance to the primary side. The conversion factor is the square of the turns ratio. The middle shunt branch is the magnetizing branch. It represents the core's ability to generate magnetic flux. During a short circuit test, Zm is in parallel with the shorted path. Since Zm is much greater than Z2, current almost entirely bypasses the magnetizing branch. Im is almost equals 0. So we simplify the model into a series combination of primary and secondary impedance. Zk equals Z1 plus Z2. This is the standard model for short-circuit current calculations, which is useful in the calculation of voltage drop, power loss, and short-circuit current. Next, we will measure the short-circuit impedance via simulation following the experimental procedures specified in the IEC standard. The transformer selected for this test has a rating of 1000 kVA. You can see the rated voltage and current parameters of the primary side of this transformer. We follow the steps on the left side of the UI. On the right side of the UI shows the experimental schematic, simulated using the transformer T-equivalent circuit. Now we officially start the test. Step 1. Close the short-circuit switch. The short-circuit switch is closed successfully, and we can clearly see the switch status in the schematic. Next, gradually increase the input voltage and monitor the primary current. Stop voltage regulation when the current reaches the rated value of 57.74A. Then record and analyze the corresponding input voltage 0.45 kV. The primary rated voltage of this transformer is 10 kV, from which we calculate the impedance voltage as 4.5%. We have now successfully measured the short-circuit impedance of the transformer. Through today's experimental session, we summarize the key knowledge points of short-circuit impedance. 1. It is experimental data. It's a value measured under standardized conditions. 2. It is a per-unit value. It is not an actual physical impedance value. Using percentages can eliminate the need for tedious impedance referrals in multi-voltage level power system calculations. 3. It is an inherent parameter. It doesn't just appear during short circuits. Physically, it represents the leakage flux. It represents the internal voltage drop when the transformer is at full load. That's all for today's video. In our next session, we'll dive deep into short-circuit impedance, exploring its real-world applications and how to make the right selection in engineering design. If you like my video, don't forget to hit that like and subscribe button. This is TechBridge. Stay curious, stay professional. See you next time.